Welcome back to ECE 340. Looks like we had a good spring break, judging from the seats, but we have less than half of the time of the semester left, but we have a bit more than half the points remaining. So we need to really buckle down this last part of the semester so that you can get in the last half of the homeworks, 6 through 10, and we'll have another exam. I believe that's on April 11th, and then we have our final exam, and I believe the final exam is the last day of finals a Wednesday. I believe it might be the last day of finals, unless the finals are still on Thursday. I can't remember how far they're going anymore. Some announcements, info sessions, if you're interested in what you might want to take for technical electives or how they're organized or what might be available to take in the upcoming school year, 2013 to 2014. I will try to discuss that in terms of what we are expecting to have offered for technical elective coursework and when they might be taught. I think you can see some of that for the fall right now, but I want to make sure that you're aware of what leads into what in terms of what does 340. If you really like this class, what can you take technical elective wise that follows on from 340? I'll pass the exams back at the end of class to determine that answer to that question if you really like 340. Maybe. I don't base it on the exam necessarily. You still have more than half the points remaining. There's a bus tour, and this is what the engineering students want when they see a bus tour. It's not a band, it's LabVIEW. I guess you could probably create a band with LabVIEW, but that's going to be on campus on Monday, next Monday. It's on Palm Drive, appropriately named since we're sort of in the spring break mode. Does anybody know where that is? It's the drive that goes into our building. It's the little section of road that goes north off of 1st or 2nd Avenue. Or 2nd Street. But it's between civil engineering and speech and hearing. It'll be in that little section. That's the location. It will be from 10 a.m. to 3 p.m. and that's the bus tour for LabVIEW or National Instruments if you're interested. Homework number 6 should be posted, and it's due not a week from today, but a week from Thursday. What I want to do today is start playing with more models. Students were curious or anxious coming into exam number 2 saying, what's this all-integrator block diagram? Are we responsible for that? You weren't then, you are now. And we'll talk about that today. But I want to now relate all of these different models that you can represent a system with. And I'll do that first with a concept map. How does that sort of look? And then we will start going between these different representations. We'll illustrate how to take a state space representation, put that into an all-integrator block diagram, and what that allows you to do. Really, it allows you to get a visual perception or concept of your system and how it's interconnected. We will then look at how we can go from a state space to a transfer function. Given a circuit, it's, let's say, maybe the first thought that you have is I'm going to take it and get a transfer function. Now I'm wanting you to think differently maybe and say, oh, I've now got a state space of that circuit. Can I now create the input-output map or this transfer function for that circuit once that I already have the state space representation? I don't have to go back and reanalyze the system. I can simply plug it into my calculator or into MATLAB or to do the hand analysis to do the operations to obtain the transfer function. And it'd be nice to actually be able to chase our tail. Meaning, if you're given a transfer function, can you create a state space representation? And we'll hopefully get through those today. And one way that we will try to get through those is by me already having some of this already written. You can have this available to you on the notes. I'll post this on D2L if you get behind in taking the notes. There's a fair amount going on here in this picture or in this concept map. This is simply a way to model, in this class, a linear RLC circuit. You might have this complicated electric circuit made up of many R's, L's, and C's. From 320, you might immediately be able to get the transfer function. So you can model that system with a transfer function G of S, and we can do that now in 340. You also should be able to write the differential equations that are governed by that electric circuit. And those differential equations may be coupled to each other, meaning voltages and currents are in all the different equations. Once you have differential equations, you now know how to get the state space representation. That was one of your exam problems on exam 2. What we want to do today is see how these are all interconnected. We will start by taking a circuit and producing a state space representation. Then we will look at how do we find an all-integrator block diagram. And if you're really observant, you can see this dashed line moving through this figure, and that's representative conceptually of the difference between the frequency domain and the time domain. You can now look at this circuit in both domains. The all-integrator block diagram we can actually model either in the time domain or the frequency domain. If we have integrators in the block diagram, we're in the time domain. If you have 1 over S's in your block diagram, then you're in the frequency domain. That's really about the only distinction in these block diagrams. State space, that's these first order coupled differential equations. That's this Q dot is equal to AQ plus BX. And we'll show then how to go from the state space to a transfer function, how to go from the state space to a all-integrator block diagram. Then we'll show how to actually go this way, but we'll do it in a slightly different path. We'll take the transfer function, put that into a block diagram, and then label the block diagram so that we can pull out another state space representation, since the state space representation is not a unique representation. You might label your energy storage devices differently than someone else. One thing to start thinking about relative to these models, the state space representation keeps track of all of the internal dynamics that's going on in the system. The transfer function really is just restricting your attention to the information between the input and the output, and you don't really worry so much about what's going on internally. And that's one of the benefits of knowing how to represent this system with the different models. Questions on that block diagram or that concept map? I'm not going to call this necessarily a block diagram. This could be just sort of a concept map where these blocks are different representations of maybe the same system, modeling it differently. Let's now return just to get us back from this relaxed spring break environment and go into the state space analysis. I gave you a circuit before we were talking about the Bode plot, and let's see if we can remember what that was. That was this voltage source, which was an input. We'll call that X of t. We had a resistor R1 and then a capacitor. Let's call this capacitor C1. Then we attached another stage, RC. There's R sub 2, C sub 2, and maybe we are interested in, just for now, let's just look at one output, and let's call it this current coming out of the voltage source. Here is a circuit, and we want to create a state space representation with that, and then we'll create a all-integrator block diagram for that circuit. And it will be a model of exactly the same circuit, it's just in a different representation. And then we'll look at the transfer function of that circuit. If we're doing a state space model for this system, or a state space representation, just by looking at that, what do you know about the state space representation in this system? Do you know anything? Can you state some facts relative to a state space representation? You have two state variables, don't you? You have two energy storage devices. You have two capacitors. You now should be expecting your system to consist of two state variables. And that's because you have these two energy storage elements. Now, if we have two energy storage elements, in this class, our energy storage elements are capacitors and inductors. We have capacitors. With capacitors, now we're interested in ice. Eli and ice, those are the two relationships that we want to be concerned with. With a capacitor, that's got the C in it, so we work with ice. This says then that the current of that capacitor or capacitors are related to or proportional to the time rate of change of the voltage dropped across that capacitor. From that I is equal to C dV dt relationship, that should indicate what you're focused on variable-wise for your state variables. With these Eli and ice, what are we focused on now in ice to create our state space representation? The voltage across the capacitor. That's the variable that's differentiated in that relationship. This now is what we want to use as our state variable. Meaning back here we could say, okay, I'm going to call this Q sub 1, and there's Q sub 2. What I want to do now is find the dynamics. What are my equations that govern the system behavior in this circuit? Or you might hear me talk about the equations of motion. Because this is a very generic representation. In this class, it's typically a circuit, but you could, once you get out of here, it could be a thermal problem. It could be an aircraft. It could be an automobile. It could be your suspension. It could be your engine control system. You now have it modeled as this state space representation. Here we're working with circuits because that's what we're comfortable with right now. How do we find these equations of motion? Now you pull out your favorite circuit technique, but probably you want to be thinking, okay, if I'm writing the equations of motion here, I need Q dot equations, don't I? I need first order derivatives of those state variables. I need a Q1 prime and a Q2 prime equation. With this circuit, I can obtain a Q sub 1 or a Q sub 2 prime by looking at the currents through those capacitors. C Q1 prime C dQ1 dt will give me the current here. C sub 2 Q sub 2 prime will give me the current in the far right downward direction. Well, if I have those, maybe I should just focus on nodal analysis and not mesh in this particular circuit. How about I now just say that I'm going to call this, let me call this node 1 and that node 2, since they're close to the different R's and C's with those subscripts. What I'm looking for the dynamics now is I need these in terms of these state variables Q sub 1 and Q sub 2. Let's now find the first one by writing KCL at 1. Here what I'm going to do is I'm going to look at that current, and that current. Those are all leaving that node, and by Kirchhoff's current law, they have to sum to 0. The algebraic sum of those nodes or those currents at a node need to sum to 0. They're all leaving, so I'll just add them up. And the current going from node 1 left is just the voltage dropped across R sub 1 divided by R sub 1. That's pretty easy. And I have that immediately in terms of my state variables, Q1 minus X of t. That's the voltage drop from left to right through or across R sub 1. And then I just divide by R1. I've already figured out what the current through C1 is. That's C1 Q1 prime. And the current going right out of node 1, Q1 minus Q2 over R sub 2. That's my first equation. KCL at node 1 then gives me Q sub 1 of t minus X of t over R1 plus C sub 1 Q sub 1 prime of t plus Q sub 1 of t minus Q sub 2 of t over R sub 2 is equal to 0. And that's now one equation that influences the dynamic behavior in that circuit. And that was found by KCL at node 1. What I want to do now is simply isolate the first derivative of that first state variable. And I can do that by getting rid of that C sub 1, or dividing every term by C sub 1, and then solving for Q1 prime of t. Meaning I'm going to now just do the following and keep Q1 prime on this side of the equality and push everything else on the other side, and then I have my first state equation. I have my Q1 prime equation. Now I have then d Q sub 1 of t dt is equal to minus 1 over R1 C1 minus 1 over R sub 2 C1. All of those multiply Q sub 1. Then I had one term that multiplied Q sub 2, and I've moved over to the other side of that equality sign. That's going to have a plus sign. That's now 1 over R sub 2 C sub 1 Q sub 2 of t. And I do have an input that drives that equation. That's the X of t term, and it has a coefficient with a positive sign, 1 over R1, running out of room, but I have an infinitely wide piece of paper, so I don't know why I'm getting so nervous about running out of space. That's for you to do, since you have a finite width piece of paper, unless you brought your roll of tape and you're taping. 1 over R1 C1 times X. That's now your first equation. Questions on that? That should be very easy, even after coming back from a week off from break. Let's now write KCL at node 2. Now I simply have two currents to sum. I have the current going to the left from 2 to 1, node-wise, and I have the current down through C sub 2. That will now define KCL at node 2. I now have Q sub 2 of t minus Q sub 1 of t all over R sub 2 plus C sub 2 Q sub 2 prime of t is equal to 0. Again, I can isolate the first derivative of Q sub 2. I'll just divide everything by C sub 2 and push everything to the other side. I now have 1 over R sub 2 C sub 2 Q sub 1 of t plus a minus 1 over R sub 2 C sub 2 Q sub 2 of t. And that now completes all of the dynamic behavior of that circuit. And if I want different information about that circuit, I can extract that information or obtain that information by linear combinations of the state variables Q sub 1 and Q sub 2 and the input X. In this particular system, that I have defined so far, the output was Y sub 1, defined to be this current going out or coming out of the top or the positive terminal of the source. And that's pretty easy to write in terms of inputs and states again. And I don't have to necessarily go back to any of my other equations. I can simply look at this circuit and say, what is Y sub 1? And if I can find that, then I have my output equation. I need to make sure that I don't have derivatives on that right-hand side. And in this case, I will not. If you do, you have all the derivative information in those dynamic equations for Q1 prime and Q2 prime. The output here, Y1, is then X minus Q sub 1 divided by R sub 1. So I now have Y sub 1 of t is equal to X of t minus Q sub 1 of t over R sub 1. That's now my equations. I have my dynamics, the Q1 prime, the Q2 prime equation, and I have one output, and that's Y sub 1. It does have an input, and it has a state variable term. If you put this now into a standard form, this is now your Q prime of t. That's a vector of Q sub i's stacked on top of each other. A times Q of t plus B times X of t Q of t is the state vector. X of t is the input vector. And we know generically that their dimensions. Oh, and let me go ahead and complete this out. Now I have the output equation is C, a matrix, times the state vector plus another matrix D times the input vector. And this should all be review. This should be making you feel warm and fuzzy at this point of the semester. This should be just very comforting to you. We're now going back to something that you should feel very good about. There's the input vector. Q of t is the state vector. And we usually make that Nevada tall, n by 1. The input is Michigan tall, m by 1. And y, I don't know that we've settled on a state for y. So let's go a little bit east. We don't want to be too geographically fixed. Let's go to Pennsylvania for y. Now we have our three vectors, an input vector, a state vector, and an output vector, and we know their dimensions. In this particular example, what was n, little n, Nevada? In this example, what was n? You could answer that right here, couldn't you? In basically our very first observation that we had. Then you could look at the circuit and give yourself the dimensions of the input vector and the output vector. One of each in this example. Let's now plug in some numbers. Suppose that we now let R1 be 1. R sub 2, let's make that 2. C sub 1 is 1. And what would you guess C sub 2 is going to be? All right, I'll throw a little bit of a trick here. I'm just pulling these out of midair, but I just want to pick some numbers so that we have numerical values for the A matrix, B matrix, C matrix, and D matrix. If you do that, Q1 prime of t, if you go through that, you end up with minus 1 minus a half Q sub 1 of t. It had two pieces in it, plus 1/2 Q sub 2 of t, plus 1 times x of t. The second equation becomes 1 times Q1 of t minus, or let's say plus a minus 1 Q sub 2 of t, and 0 times the input. And the output y of t, now that we let r sub 1 be 1, we were dividing by 1, and we had x minus q sub 1 for y. This now becomes minus q sub 1 of t plus x of t. And we can now plug these in to our standard representation. We have minus 3/2, 1/2, 1, and minus 1. Our input matrix now is 2 tall and 1 wide. A is always square. And we may actually call that our system matrix. B is 2 by 1. The input matrix. And our last relationship is the output equation, which we said was y1. It was now minus 1 times q1, no q sub 2, and x of t. Our output matrix C then is 1 by 2. And our direct feed-through matrix D, in this case, is a 1 by 1 matrix or a scalar. Questions on that? We now have a system that we can play with. One thing, if you're into linear algebra, you could compute the eigenvalues of this system matrix, and those are actually the poles of your system. And what do you know about the poles of your system? Where have you seen those before? Now, if you were taking a linear algebra class, or maybe in 310, did you study eigenvalues in ECE 310? Now you have a reason for knowing what one way of worrying about eigenvalues. That's now giving you the dynamic behavior, the natural behavior of your system. That's the poles in your transfer function. Those are the roots of the denominator. Let's now go to this concept called the all-integrator block diagram. Now that we're back and feeling warm and fuzzy, let's move a little bit away from that and get into something that you need to start developing that same feeling for, and that's the all-integrator block diagram. This is now a graphical or a pictorial way to show the interconnection of your system. And we're going to build it based on this description or this state space representation. These numbers are going to appear in this block diagram, this all-integrator block diagram. And the all-integrator block diagram is going to consist of summing junctions, gain blocks, and integrators. And really, it's going old school. This is now an analog computer. Once we draw this all-integrator block diagram, this will actually be an analog computer. Instead of what you now play with, I was going to pull out my phone, I guess. Instead of a digital computer, now you can think of an analog computer. Now you could build, if you had these equations of an airplane, now you could create a system, an electrical system that models that airplane's dynamics. And now you could have it on your workbench. You wouldn't have to go out into the field and start playing with this airplane. Now you could fly it on your bench because it's now just some op amps with integrators, summing junctions, and gain blocks. I said you're going to start feeling warm and fuzzy. I want you to feel good about what we're doing. Now we're playing with blocks again. Maybe you did this in preschool, right? You didn't realize your teacher was setting you up for differential equations and analog computers. Now these blocks have integrators, gains, and summing junctions, and now we're going to put those together. With this system, how many integrators do you think we want to throw down on our piece of paper? We really are wanting to have, I said this was an analog computer, we really are wanting to solve for Q sub 1 and Q sub 2. We want those to come out. We want to build a system such that we could inject an input signal X, and out the other end is going to come the output Y. We want to build a system that has that characteristic, and it's going to have the dynamics and interconnection structure determined by this electric circuit. We have two derivatives, so you would expect to have two integrators. We want to integrate Q1 prime, and we want to integrate Q2 prime. And this is why we studied the calculus. If you integrate Q1 prime, what are you going to get? Q1. If you integrate Q sub 2 prime, this is really hard stuff. What are you going to get? Q2. That's all there is to it. We have two integrators. So here's our block diagram, and the way that this, I'm going to draw this one just because of the way I can anticipate it's going to be interconnected. I'm going to put one integrator here. There's one of my blocks. And I'm going to stack another integrator right there. And conventionally, I mean, you have to follow the arrows, but typically the left is the input side and the right is the output side. But if you have feedback pads, you kind of have to look around and see what's the input and what's the output. I'm going to now say the left side of that integrator is the input to that integrator. And really, I said I was trying to solve for Q1 of t and Q sub 2 of t, which says, why don't I just call this signal coming through in that line Q sub 1 prime. Likewise, I'm going to create down below another signal, or I'm going to label this signal coming into this integrator as Q sub 2 prime. Now, if I have Q1 prime going in, you just told me from your years of calculus study that you integrate Q1 prime and you get Q1. That's pretty hard, isn't it? Don't you wish your calculus was that easy? That you could play with blocks with calculus? What you want to do is develop insight and intuition with all of your engineering skills. And this is one way to start to do that, to start to feel comfortable with what's going on. Now you're translating these coupled differential equations into a block diagram, into a picture. These are relationships that you should feel comfortable with. That should be clear. Now we have to build up what actually produces or makes Q1 prime. Well, that's this signal. But now I'm going to say, well, that's the linear combination or the sum of some other signals. And all of those other signals are included in my state space representation. Q1 prime, I already know what that is. That's just minus 3/2 times Q1 plus 1/2 Q sub 2 plus X. Those now, all three of those signals need to come into that summing junction and create the output of that summing junction, which is Q1 prime. Does that make sense? I go back to my block diagram and I say, okay, Q1 prime I said was minus 3/2 times Q sub 1. So I just pull Q sub 1. I have it available to me. I gain it up by a minus 3/2, and I put it in as an input to that summing junction. Then I said another signal going in to create q1 prime was 1/2 q sub 2. So now I take 1/2 and I find q sub 2 down here. I scale that by 1/2 and now I put that in as another input signal to that summing junction. And finally, I need the input x of t, and I'm assuming that I have access to the input. I have the input, I'm going to inject that into this block diagram, and out's going to come my answer y of t. And that's all on my circuit in the lab. And that might be modeling these suspension dynamics of a vehicle, for example. And now you have it on the bench. If that's how I create q1 prime, it should be pretty clear how I create q sub 2 prime. I now simply come over here and I just read off what you've now set it's equal to. There is no input coming in. We could with a zero gain if we wanted to be very generic. We have q1 minus q sub 2. I now say, well, q sub 2 prime is some linear combination of signals. It's now this q sub 2 scaled by -1. And it's also, why don't I just pull this off? That's still q sub 1. Whoa, what happened to my 1/2? I was playing so much with my blocks that the paint rubbed off on that 1/2 on that gain. Sorry. So I painted it up again for you. If you were falling asleep, heaven forbid, but if you were getting tired and you missed that, doesn't really matter, does it? There's q sub 2 prime. And notice that I tried not to make this look like there was a connection between those two lines. That's the jumper over those two lines. So I wouldn't be soldering those two together. That is now my electric circuit in a block diagram form, or that's the dynamics. I now need to figure out how am I pulling that dynamic information off to create the output. What is my y of t? I just defined one output. I could have defined 10 for this circuit if I wanted to, and Pennsylvania would have been 10 tall. Here, Pennsylvania is 1 tall. Pennsylvania is now -1 q1 plus no q2 plus the input x. I now come down to my block diagram and I say, you know what? I have some output. Let me just change the color here. Let me say this is y sub 1 of t. And I'm going to create that by some linear combination of states and inputs. And in this case, I actually take q1 and scale it by -1, and I take the input x and I scale it with 1, and I add those up, and that creates my y sub 1. Now, as a system, this is my electrical circuit written as an all-integrator block diagram. You inject a signal, x, as the input. That's the voltage that you're exciting this system with. And it shakes around and moves, and now the paint's gotten blurred, hasn't it? It came back to life. It shakes around. How does it shake naturally? What influences the shaking? It's in there. The dynamics of x, or the waveform of x, but what else? How does this naturally shake? If I simply put some initial conditions on this system, which would mean, let me just set Q1, that's the voltage of one capacitor, and Q sub 2, let me assign those some value. flip the switch and see what happens, how will they shake? It's going to shake according to the poles of your system, right? And those were the eigenvalues of your A matrix. You find those eigenvalues of the A matrix, and maybe they're -2 and -6. Now you have modes of e to the -2t and e to the -6t. If they were complex, they would be complex conjugate, and you would have damped oscillations for your natural behavior. And you would have the dynamics of x. Questions on this? Now you have an analog computer, and you could build that in the lab. What did I say we were going to do next? You could now build this up with op amps, resistors, and capacitors, and you could solve those differential equations. Yes, sir? Correct. So the question was, the output in all of its glory could have been that, right? Y1 could have been some linear combination of Q1, Q2, and X. That's the generic expression for Y. In this case, there was no piece of Q sub 2 making up the output. So if you had this generically configured, you would want to put a 0 there for the connection between Q sub 2 and the input to that summing junction for Y sub 1. Question? So now I'm not going to worry too much about the dynamics of this. I'm just going to assume that we can build an integrator network. And that's just this op amp with an R and a C around it, right? So I'm not going to worry too much about how I do that. For now, I just want to know, oh, I could do that, and I would want that dynamic to be such that it effectively solves this circuit. So if you might have included some damping in your integrator, and you might not want that to be very fast, but you don't want it to not be there because you maybe want to create a stable system. But I'm not going to worry too much about that. I'm just going to say, here's an ideal integrator, 2 of them, here's some gain blocks, some summing junctions, and now here's my system. And for generic assembly, that's going to work pretty well. Other questions? That's now one direction in this concept map. We've now gone from a state space representation. If I give you a 10th order state space representation, you should be able to create an all-integrator block diagram. How many states would you have? Or how many integrators would you have in a 10th order differential equation? You're going to have 10 integrators. It's going to be an interconnected mess, possibly, but there's probably going to be a lot of sparsity, a lot of zeros. Yes? You could. So now the way to think of this is to just say, oh, do I know how to build a gain of -3/2? And you do, out of an op amp and 2 resistors. So now you have this inverting op amp configuration to give you a -3/2. Maybe you have a non-inverting op amp configuration to give you the 1/2. But you can build all of these out of electrical parts if you wanted to. In MATLAB, they have another block diagram package called Simulink. And you could build up a Simulink model with this kind of interconnected structure. We won't do that here, but I'm trying to get you to think about what you have in front of you. What I want to do now is I want to take this state space. We've gone from state space to all-integrator block diagram. Now let's go to a different model. Let's go to something that we already know how to create directly from the circuit. Let's get it indirectly by starting with the state space, since we've analyzed our circuit this way now, and get the transfer function. And now if your buddy said, oh, I've got the transfer function of this circuit, you go, well, I worked it the long way and I've got the state space, let me check. Now you can check your transfer function with his transfer function. Let's now look at this process. Again, this is the first concept map diagram of the lecture. Let's now look at state space to transfer function. Let's go ahead and start with our standard form. Our standard form is this vector of derivatives, a q of t plus b x of t. The output y of t is now c q of t plus d x of t. We now want to find a transfer function description of our system. We want to find, this is a time domain, dynamic system behavior of our whatever system we're playing with. We now want to find the transfer function between the input x and the output y, and that will be a frequency domain description. And how do you take time domain into the frequency domain? So we're going to now Laplace transform this set of equations. Let's now Laplace transform these differential equations. What happens when you Laplace transform a derivative? And let's do it in all its glory. S times the variable, right? And in this case, we have variables, Nevada of them, don't we? We have Q sub 1, Q sub 2, Q sub 3, all the way up to Q Nevada. And now we want to take it in all its glory, so we want to contain or capture its initial conditions. But if we're going into the frequency domain, let's capitalize things in the frequency domain. So we now have S times the Laplace transform of little q of t. We'll call that capital Q of S. But capital Q of S is what? That's a tall, Nevada tall, one wide vector. And that's a Laplace transform of each of those variables in the state vector Q. Little q sub 1, Laplace transforms into capital Q sub 1 of S. That's the Laplace transform of that state variable signal. This is now a tall, thin vector. This is S times Q sub S minus the initial condition at time 0 minus. But that initial condition is the time value of that state vector, each of those variables. In that example, that would have been the initial voltages on those capacitors if they had non-zero initial conditions. This now we will write as little q of 0 minus. And this is when time is equal to 0 minus. That's now the Laplace transform of a vector, a differentiated vector in all of its glory. S times Q minus the initial condition. Now we need to Laplace transform capital A Q of t. A is a constant, isn't it? Once we have values for our R's, L's, and C's, capital A is a fixed constant. It's a linear time invariant system that we're playing with. A is a constant matrix. We Laplace that slides in and out of the Laplace transform operation. It doesn't impact it, and all we have to do is Laplace transform Q of t. And we agreed to call that capital Q of S. Now we can proceed with these Laplace transformed expressions on the right of the equality sign. What's the Laplace transform of B x of t? B is a constant, isn't it? So the Laplace transform slides right through that constant matrix, and we have to Laplace transform little x of t. And we just agreed to call that capital X of S. What if we Laplace transform that output equation? Are there any dynamics there? Any derivatives? No, this is just a linear relationship, and we can just Laplace transform that directly. We can change the lower cases to capitals, and we're done, essentially. We go from directly the time domain into the frequency domain. It's a linear relationship in both domains. We now have y of s, capital Y of s, is equal to C, capital Q of s, plus D, capital X of s. And now what we want to do, we want to find a relationship between X, capital X, and capital Y. And if we're looking for the transfer function, we don't even worry about the initial conditions. Let's keep track of it as we go so that we can actually see the entire solution in the frequency domain, and then when we go into the time domain, we could find the complete solution in this matrix representation of our system. Now we have to do something a little bit maybe not so warm and fuzzy right now. S is our frequency variable, isn't it? That's a complex number. That's a complex frequency number, and it's a scalar. We have a scalar times a vector. Here we have a matrix times a vector. If I multiply A times Q, what do I produce? A is how big? Square, isn't it? Nevada by Nevada. I multiply Nevada by Nevada times a Nevada by 1 vector. What's my answer? A Nevada by 1 vector. This right-hand side is now a vector, isn't it? What's over here? A scalar times a vector. Oh, good. At least my quantities on either side of the equality are consistent. I just have n by 1 vectors on both. B, Nevada tall by Michigan wide. But I'm going to multiply that by a Michigan tall by 1 wide input vector, and I'll end up with a Nevada by 1 vector. This product better be consistent or compatible with all of the other products or expressions in that equality or in that equation. And little q of 0, that's a Nevada by 1 vector, column vector. But now I want to maybe combine my capital Q terms. I have a scalar S and a matrix A, n by n. S times Q. I can create something that looks exactly the same by putting in that identity matrix, which is square, and it's Nevada by Nevada, big. This is just ones on the diagonal. And I haven't changed this product, have I? But now I have a matrix SI that's n by n times q. Let me pull that other piece to the left-hand side, which was minus a q of s, and let me put the initial condition on the right-hand side. I'll add that to both sides, plus b x of s. Are we okay with that? This is now just a placeholder, and it's squared just like A. It's compatible with A dimensionally. Now I can factor out that common vector, capital Q of S, from those two terms on the left. I can now say, oh, I now have SI minus A times Q of S is equal to Q of 0 minus plus B x of S. But if I could get rid of Q of S, capital Q of S, in this output equation, I would have a relationship between X and Y. And I can find capital Q of X if I pre-multiply every term in this last equation by SI minus A inverse. But now I'm playing with matrices, so I have to do everything properly. I'm now hitting everything on the left with this matrix inverse. It goes away here, but it introduces itself in two places on the right-hand side. Yes, so this will always be invertible. We now have SI minus A. S is a complex frequency variable. It's going to have weird results at the poles, at the eigenvalues of A. If you remember your linear algebra, if you solved SI minus A equal to 0, or the determinant of that equal to 0, that would give you the values of S that satisfy this equation, and those S values are your eigenvalues of A. So that's okay. That's going to be consistent with what we've been playing with or talking about as far as the poles of our system. First, let me just write this down. Here we have capital Q of S is now SI minus A inverse times Q of 0 minus plus SI minus A inverse B capital X of S. Yes? So now what we're keeping S as a variable. So right now this is symbolically going to have an expression or a value. Now we can find values of S that will cause that to blow up, and those will be poles in our relationships. But symbolically for us, this is okay. SI minus A. If A has an eigenvalue at 0, this is S all along the diagonal, isn't it? That has full rank in terms of S. That's n by n. So really no matter what A is, we're okay, because we now have this SI in there. Now, I have a Q of S expression, and if somebody just wanted the dynamics of the state variables, you could inverse Laplace transform this. This is a matrix, but you could get all of your dynamics of your system state variables by inverse Laplace transforming this expression, given initial conditions and the forcing function little x of t that we would have its Laplace transform of. We want to now find this relative to the output, and the output was right here. Here's my output equation. I'm going to replace this capital Q with what I just wrote down, so it's going to get a little bit messy, big, but it's not that complicated. I now simply have to pre-multiply that expression for Q by C on the left and add in dx, and I have my result. Here's what I need. Now I have y of s is C times Si minus A inverse Q of 0 minus plus C times Si minus A inverse B x of s plus the d x of s. And now I have my total response if I were to inverse Laplace transform that. This piece is the response due to the initial condition, and I could call that the initial condition response. Now, what I'm going to end up with is I'm actually going to rewrite this as, let's say, C times Si minus A inverse B plus D, just factoring out the common vector, capital X of S, from both terms. That's now the same expression as I have here. But now this piece in the square brackets, that's what I was looking for. That's my transfer function, which if I threw away my initial condition, that's the transfer function between the input x and the output y. This is now what I was wanting. Here's, let's say, g of s, which is the transfer function. But this piece right here, including the x, is the forced response, and now I have my total solution, or total response, the sum of the initial condition response and the forced response. And I found it in the frequency domain. Now, if you wanted to play in the frequency domain, you would be on that left-hand side of the very first concept map that we started with today. And now we have, if somebody gives you the state space matrices, A, B, C, and D, you can build up the transfer function. You simply have to compute this expression. Let's write that down. That's such a fundamental result. We don't want to forget it. Let's now say, oh, we now have our transfer function. Capital G of S is equal to C, Si minus A inverse B plus D. And that's how, if we start with, and you wouldn't have to now rederive this result, now you could have this relationship on your notes, and if you now derive the state space representation, you could say, oh, I know how to get the transfer function. I just plug in the A matrix here. What's this? That's your complex frequency variable S, but how big is I? It's Nevada by Nevada, isn't it? It's the same dimension as A, your system matrix. You invert that matrix, and that's going to be a symbolic matrix inverse. But you could do that with your TI-89 if you want. Then you pre-multiply it by the output matrix C. You post-multiply that symbolic expression that has an S floating around by the input matrix B. If I had one input and if I had one output, what's the size of this Well, what's the size of D? If I have one input and one output, what's the size of my direct feed-through matrix? It's 1 by 1. That's a scalar. It's a big matrix. It's 1 by 1, isn't it? How big is C, Si minus A inverse B? 1 by 1. What if my system was 10th order? What's the dimension of this term? 1 by 1, isn't it? But what's downstairs? How many poles do I have? I have 10 poles, don't I? I now have a 10th order denominator and a potentially 9th order numerator, which I will now add to a 1 by 1 constant. And that will give me my transfer function, capital G of S, for a 10th order circuit. And it falls out of having the state space matrices. Oh, I should have told you to close your eyes so you wouldn't get sick as I was scrolling back, but because I don't know how close we are to spring break. Still too close, huh? All right. Where did we start? We started with a circuit, didn't we? We found the equations of motion, the differential equations, and we put those into a state space representation. Then we went to an all-integrator block diagram. Then we said, oh, we can get the transfer function. Instead of going this path directly, we could go this way. Couldn't we? Now what we want to do, and since we have a few more hours left, we want to start here and go here. And we will now just go from here to there to there. And then we will have a way of finding our tail, right? We will have been able, and we will show how to go here to there, and once we have this, we could go here, or once we have the all-integrator block diagram, we could go to differential equations. We have a way of relating all of these different representations or models. Questions on that?